going to begin talking about polymers, polymer structure, properties, and the interaction morphology with those properties. So we'll look at the 4 basic structures that you need to learn: vinyl molecules, develop understanding the difference in thermoset and thermoplastic polymers, and introduce some important concepts: glass transition temperature, crystallization, crystal melting, and so on. All right, so first of all, polymers are really organized, can be broken down into 3 categories based on price, into 2 categories based on structure, and then a number of categories based on application. And you need to have some broad understanding of what these are. Price is a big driver. Commodity polymers generally going to run less than $1.50 a pound or so. There's a little bit of wiggle there, but commodity polymers such as polyethylene, polypropylene generally have prices well below $1 a pound. Engineering polymers are generally higher performance materials. They carry a higher price tag. That higher price tag doesn't just buy the materials, it also tends to buy technical support and engineering data and other things, so that those materials can be used in applications that require more information. And often when dealing with engineering polymers, if you have a major question about the material or about your problem, you actually have access to professional teams, tech support, development teams, R&D people that the resin manufacturers or resin suppliers actually maintain to help customers. When you're dealing with commodity polymers, you're not paying a whole lot beyond the cost of the material, and tech support is generally only available if you're a very large customer buying large quantities of those materials. Generally, you're going to be a little more on your own if you're not a significant customer. There's a good deal of data available online, usually, and resin manufacturers make a lot of data available, but they don't have the resources to help small customers out in commodity materials. And then you have finally specialty materials, specialty polymers, and these upwards of $5 a pound, and they can run literally to $1,000 a pound. And these may be specialized electronic materials, very unusual adhesives, or sealants. You run into medical polymers, materials used in the body or for drug delivery. And these can carry very, very high price tags. And often you're quite happy to pay the price because they're specialty and they allow you to do things there's no other way to do. And so economics and the economics of these things are a little different than your consumer goods. Right, polymers are also broken down by application. And you have to be aware that if you're working with a particular chemistry, you're using, let's say, polyethylene, so we're looking at here, you may use polyethylene in fiber form. This is fishing line. It's a polyethylene product. You may be using polyethylene in bulk. We call this a plastic application, sheets. You may be using it as a film. And if you are trying to get tech support or you're trying to contact the relevant people at the resin manufacturer, they will be usually divided by market, whether it's a film coating market, adhesive market, plastic market, whatever. And so you understand what business you're dealing with rather than what resin system. Now, some resin systems are very flexible. That is, have a great variety of applications. So polyurethane chemistry, for example, is a fantastically diverse system. And of those 5 categories I just showed you, it's used in coatings and films, it's used as an adhesive, it's used as an elastomer, and then as a plastic and foam, which you're familiar with, but also filled with fiberglass. It's used to make body panels and other parts of automobiles. So you have a large range of uses for the same chemistry. And if you were talking to somebody that's in the polyurethane business, if they're in the coatings business, they're not necessarily going to be able to help you with your foam problems or what have you. So understand where you fall. All right, where do these magic materials come from? Well, polymers are built out of essentially this list of elements. The vast majority of the plastics that you have in your daily life really consist almost exclusively of carbon and hydrogen, occasionally some oxygen, nitrogen, thrown in. If you have non-stick cookware, non-stick coatings on your electric skillet at home or on your pots and pans, that's probably a fluorine-containing polymer. And high temperature flexible rubber cookware, baked pans, that kind of stuff are silicone-based polymers. And sulfur and chlorine show up in a few systems. But most of the polymers in your daily life are primarily hydrogen and carbon. We call them they're hydrocarbon-based materials. So the key to polymers is carbon. Carbon's magic. Atomic number 6, so your valence structure is 2s2, 2p2. And if you think about that, the p orbital needs 6 electrons. That means that 2p shell is missing 4 electrons. That's not a very stable situation because it basically means one of the p orbitals has no electrons in it and the other 2 are half filled. So what carbon does is it forms a hybrid orbital called an sp3 hybrid. It makes 4 of those, each of which is capable of holding 2 electrons, and they're arranged tetrahedrally. That is, the angles between all of them are exactly the same. And then each of those will get 1 electron that's native to the carbon, and then they can pick up a shared electron from one other atom. So carbon can bond to up to 4 other atoms. And that makes it the basis for life. It also makes it a wonderful building block for polymers. The carbon-carbon bond is itself quite strong, and that's all diamond is, the hardest material known to man. And simply carbon atoms bonded to other carbon atoms with that wonderful covalent bond. So at least within the polymer chain where we have carbon-carbon bonds, we have tremendous strength. Now, a couple ways to build things. The simplest is to start with building blocks that we call MERS, monomers. And what's usually going to happen in that MERS will have some double bonded carbon in the backbone or in the chain. We may have some other kind of bond or a structure where a bond can be broken by the formation of a hydroxyl group or something else. The key here is leaving carbon atoms with unpaired electrons. That's all these bars represent. If we break this bond, this carbon gets the electron it was sharing, this one gets its electron back, and now we have what are called free radicals. So essentially polymerization or addition polymerization is going to begin with something like ethene or ethylene, form free radicals, and then, well, this free radical can bond to that free radical, and we're going to propagate a chain. The end of this, you have additional free radicals. This is going to tend to make a linear polymer. Now, funny things can happen, and branching can develop depending on the raw materials you're working from, and so on. So things may not be perfectly linear, and we'll be dealing with that in a little bit. But in the ideal, obviously, we're building a long chain molecule. Now, addition polymerization is favored particularly for biological materials, where it's going to go into the body or be used in a biological environment, because this process tends to produce a very clean material. If it can be done in the gas phase and you have no solvents present, no water present, simply going to have polyethylene and nothing else added. Now, there's several categories of polymers. There are a number of structures. I want you to learn 4. You're going to learn the 4 simple vinyl polymers, the simplest of the vinyl polymers. And the simplest vinyl is polyethylene. This is my building block. The braces mean this is just a repeat unit, and we're actually going to build long chains out of this. But it's simply this unit repeated over and over again. Obviously 4 hydrogens, 2 carbons. If we substitute for one of the hydrogens, put a methyl group in, we get what's called polypropylene. That is, the building block is a 3-carbon molecule, and the 3-carbon hydrocarbon is propylene. But the chain actually continues on these backbones, and so you can think of this as this CH3 is replacing one of the hydrogens on this backbone. The other 2 vinyls that you need to learn are polystyrene. One of the hydrogens in the backbone is replaced by a benzene ring, which is a ring of carbons, obviously saturated with hydrogens. And then the other is polyvinyl chloride. So we substitute one of the hydrogens with a chlorine, and PVC, it's water pipe, and a number of other applications. We'll look at that. Okay. So what we end up with are these long chains that have, in the backbone is carbon atoms, and then off the side we have various things hanging. Now, this is a bunch of spaghetti noodles, and the question comes up, what is going to hold these together in a three-dimensional structure? I'm going to build plastic parts. Even in a film I have 3 dimensions, and a long string is really simply almost a one-dimensional object, right? You really would just want to load it axially or along the length of the molecule. So what holds them together is 3 things. The molecules get tangled. Think of this as a big pile of ropes, and you pull on them, the ropes get tangled up. So we have entanglement mechanism. Van der Waals forces, secondary bonds, are going to hold the molecules together. And then it's also possible in polymers to introduce primary bonds to link the chains together with other covalent bonds. So that leads us to our next major subdivision of polymers into categories. And this is kind of the ultimate division. Polymers fall into one of 2 categories. Thermoplastics have only secondary bonds and entanglements holding the molecules together. And what that means, those bonds can be restructured easily, so these are easily reshaped, or they are plastic materials. Thermoplastic means you add heat and you can reform the polymer. The issue with thermoplastics, they are not that expensive necessarily, the resins, and there's many of them that are very cheap, but they generally require fairly high pressures to get precision parts in the reforming process, and so we're often talking about fairly expensive tooling for making these materials. But the ability to heat them up and reform them means that scrap can be ground up and remelted and reused turned into final product, so they can have very low waste levels when we work with thermoplastic. The other kind of, or family of polymers, are thermosets. And in a thermoset polymer we have both primary and secondary bonds between the molecules. So we have entanglements going on, we have van der Waals bonds going on, and we're going to introduce primary bonds to hold the molecules in place. Now, traditional thermosets cannot be reshaped. There's some interesting new chemistries people are playing with where you can unlink these primary bonds that you've formed, but none of those are commercial as yet. The nice thing about thermosets is because we can start with fairly small molecules, because we're going to build them by creating primary bonds, we can end up with raw materials that have very low viscosity. That is, they pour, they flow easily, which allows us then to do molding on tooling that can be very cheap. Plastic tooling, wooden tooling, rubber tooling, all of those can be used because we don't have to use a lot of pressure to make the thermoset flow. Since the molecules are very short, they're going to give us a very low viscosity system. So thermosets often get used where we only need to make a few parts, and tooling costs would be too high to work with thermoplastics. All right, so to summarize, our polymer categories are broken down. Thermosets versus thermoplastics. The thermoset is a network polymer. A thermoplastic is going to be a linear polymer. Thermosets will be fixed. Thermoplastics will be reshapeable, and the name kind of gives it away. Plastic, formable, set, fixed. Okay, so thermoset, here we have an example, a schematic of a thermoset idea. And basically I can get anywhere on this molecule and I can go anywhere else in this whole molecule without leaving the molecule. The chain, this is a 3-dimensional molecule, it's all connected together. In thermoplastics, the molecules cross over each other, but this chain here, for example, does not connect to any other chains. It's a chain by itself. Now, chains can do funny things. They can fold back into tightly packed regions of what we're going to call crystalline regions, what are in fact crystalline regions. But the interactions between the molecules are some variation of a van der Waals bond and then entanglements which can occur. Okay. So let's look at a formation of a primary bond. This is the epoxy reaction. And you buy epoxy at the hardware store, at Walmart or Target or whatever. It's a 2-part system. And the thick part is usually a diglycetyl ether of bisphenol A. This is bisphenol here. And we're going to build a chain that's a bunch of these bisphenols. And then at one end of the chain, we're going to have this little funny structure. It's called an oxyrane. and the other end a bisphenol with an oxyring on the end as well. This length can be varied, and so the liquid epoxies can get long enough chains that they're no longer liquid. They can be semi-solid at room temperature. In the lab, you will be using adhesives, film adhesives that use an extended or a long chain epoxy, and so they're tacky, solid, kind of waxy material at room temperature, not a liquid. But we also have liquid systems that you literally mix two liquids and stir. Now, just a note, this is organic chemistry notation for molecules, and since we know these are hydrocarbons, we don't write the carbons on the structure. So every place you see a junction, there's a carbon. Carbons at all these places. These are double bonds between carbons in the benzene ring, and there's obviously carbons here, and carbon here, carbon here. And so there's a carbon at each junction, and then you should supply the missing hydrogen, so each carbon has 4 neighbors. So the carbon here between, or to the left of this oxygen, obviously it's only bonded to the oxygen and another carbon there, and so it must have 2 hydrogens attached. This carbon's bonded to the oxygen and a carbon here, so, and to this carbon, so obviously there's just 1 hydrogen attached to that one. Again, here's 2, so I got 2 carbons, and so on. Each of the carbons in the benzene ring has 1 hydrogen, except for this carbon, which doesn't have it. So you can construct the overall structure, but this is much cleaner than writing the C's, as we've done down here every time. Okay, so the epoxy that you probably bought at the hardware store is usually cured with an amine of some type, some primary amine. Or it might be a primary and a secondary amine. We'll just look at the primary amine as our model. A secondary amine is going to have the ammonia in the middle of the molecule, and so it's just an NH1, not an NH2, but basic mechanism is similar. So R simply means I've got some organic molecule hanging off. Same thing here, I've got some organic molecule, probably some version of a bisphenol. And then there's the oxyrane group, which is this little functional group on the end. And what's going to happen if you decompose this is essentially this oxygen is going to lose the bond with this CH2 on the end of the molecule. It's going to strip a hydrogen from this nitrogen, take that hydrogen over, got an OH, okay? Now this oxygen is bonded to the carbon here, and it has a hydrogen. This bond is broken, which means the CH2 has a free radical. This nitrogen has lost a hydrogen, so it's now got an unpaired electron or a free radical. And so that nitrogen is going to bond to this carbon, and we end up then combining these molecules. Here's my NH. We flipped them. This one's going over here, and this one's going here. Okay, and it's going to bond to the CH2 that's at the end of this molecule. All right, so that is an example. We've taken 2 molecules. There could be all kinds of stuff at the end of this, and this could be quite a long chain, and we've connected them into a single molecule with a primary bond. Now, we can also do what's called cross-linking, and this is perhaps the oldest and most significant cross-linking mechanism. If you take polyisoprene, which is natural rubber, comes from the rubber tree, mix it with sulfur and heat it, the sulfur ring, sulfur is going to be a ring structure like this, it's going to break open, and the sulfur will form what are called cross-links. It'll connect these long chains of isoprene with bonds, covalent bonds between the chains. So it's sometimes called a ladder polymer. Looks like you're building a ladder, but cross-linking is the more general term. The effect of this is to lock these very, very flexible chains into position with respect to each other, keep them from sliding. So natural rubber has a stress-strain curve that looks like this. As you finally get all the molecules aligned, it starts getting stiff. When you vulcanize it or cross-link it with sulfur, you then get a stress-strain curve. Got a decent modulus, right? It's rigid from the beginning, or stiffer from the beginning. And this was the key to making automobile tires that could support advancements of automobiles to drive at high speeds. Natural rubber tires don't do very well when cars go fast. They heat up and they tend to blow. And the cross-linking enabled the modern automobile tire industry to emerge. Okay, so what happens when we cross-link? Well, you can memorize all of this stuff, but what I hope you'll do is you'll just look through these effects and say, okay, that makes sense. So if we cross-link or network the polymer, we are adding primary bonds to the polymer. Now, primary bonds are stiff. Secondary bonds are not. So when I add a primary bond, I'm going to bump the modulus because primary bonds increase the stiffness of the material. Similarly, because we're tying the molecules together, it's very difficult for them to, or it becomes more difficult for them to move as we add crosslinks, and so the strength of the polymer is going to go up. Because these are primary bonds holding them together rather than van der Waals bonds, the polymer is not going to respond to temperature changes as much, and it's going to be more thermally stable, will not flow at elevated temperatures easily. Because the molecules are held together by primary bonds rather than van der Waals bonds, you'll find that molecules don't dissolve as easily, and it's more difficult for chemical reactions to occur. They're kind of protected by those primary bonds. It will, however, adding crosslinks will in fact lower toughness. And then finally, it's going to drive the glass transition or temperature, or T sub G, higher. It's going to make the TG go to higher temperatures. Now, what is the TG? So we need to introduce the concept of the glass transition temperature. The glass transition temperature, in a simple sense, can be thought of as the temperature where van der Waals forces essentially break down. Now, that's not completely what's going on, but it's a helpful way to think about it. Basically, at the TG, you begin to get large-scale molecular motions. The 30, 40 repeat units can start wiggling around. The molecules become mobile. And so polymers go from a glassy, rigid behavior. So if you're wearing glasses, you probably have polycarbonate lenses. That's a polymer that's in the glassy state, so it's hard. And if you took that above its glass transition temperature for polycarbonate, that's somewhere around 150 degrees, then it would become a rubbery material like the shoes that you probably walked in on that have synthetic soles. And so that is a polymer that is above its glass transition temperature, and the molecules are mobile, and so it behaves in a rubbery fashion. If I cooled it down below its TG, the molecules become locked in place, and it would become a glassy material like your eyeglasses. Okay. Now, in amorphous polymers, it's really important because you usually cannot go above that temperature in amorphous polymers. They become unusable. However, where I have a cross-linked system, as in natural rubber that's been cross-linked, or in any thermoset, you can often operate above the TG because those primary bonds hold things together even when the van der Waals bonds are broken down. There are other polymer categories we'll be talking about, particularly semicrystalline or crystallizing polymers, where the TG is maybe important because below the TG the polymer becomes brittle, but it isn't as much a limit on surface temperature. So the key here is, below the glass transition temperature, the polymer is a rigid, glassy material. Above the TG, it becomes rubbery and flexible. Now, this is about motions, and so the van der Waals bonds are one way to think about it, but you can ask, what's going to affect the TG of a polymer? It's going to be affected by structure. So let's take a simple backbone, polyethylene, so carbon backbone, and what happens if, and it has a TG of about minus 120 degrees Celsius, about 150 Kelvin. What happens if I stiffen this up by throwing in a double bond? Well, the TG goes up. Or if I throw an oxygen into this backbone, it makes this backbone even less flexible. The TG goes up even more. What if I throw in essentially a truss? This is polyvinyl formal, and if you think of this is really stiffening this backbone, keeping it from moving. TG goes up even higher to 105. And then in polycarbonate, all kinds of crazy stuff. We've got oxygen, like you have in polyoxymethylene. We've got side groups hanging off here. These benzene rings are big honking stiff things. And the TG gets even higher. So one way to think about the TG is that the rubber molecules are dancing. And we've gotten rid of van der Waals restrictions, and there's enough room around the molecules for them to dance. Now, if they have a really stiff backbone, they don't dance very well. They need a lot of room for this molecule to wiggle around, and so I'm going to need a high temperature to create that room for the molecule. Okay? Again, extending the idea of freedom of motion. What happens if the side group on the backbone of this chain is polar? What if I don't have a neutral molecule? Well, polypropylene has a side group that bumps the TG somewhere around minus 10 degrees, maybe minus 20. So quite a bit higher than polyethylene's TG of minus 120. When I throw a chlorine in here, the chlorine-carbon bond is somewhat polar, and that drives the TG to 87. If I throw carbon-nitrogen, make polyacrylonitrile, this is even more polar, and so we drive the TG up a little higher. And you might think about this, basically everybody on the dance floor has a big magnet in their right hand. And so if they get close to other dancers, it's going to repel. And so it's hard to dance when the magnet's pushing on you. So you stay farther away, or you have to be farther away for the dance to go on. Okay? We can take that side group idea and simplify this, get rid of the distance, the force of the distance, and let's just ask, what happens if you don't bring a purse to the dance, or you bring a little purse, or you bring a great big giant handbag? Well, if it's just you dancing, TG minus 120. Small purse that interferes with the dance, minus 20, and you can take a great big handbag or suitcase, and now it's got to be really hot. You need room on the dance floor to swing that big purse around. Okay? So glass transition temperature, heavily influenced by the strength of the van der Waals bonds in the molecules, or between the molecules. That's another thing that this polar thing does. I can have stronger van der Waals bonds here as well, and so it's holding the molecules together, and then those negative charge centers kind of repel other charge centers, and so it restricts the motions once things get going. So kind of a dual effect. All right, so the key here is when the molecules become really mobile, we have rubber behavior, and when they're kind of locked in place, we have glassy behavior. All right, now can we alter the glass transition temperature in ways besides structure? Well, yeah, we can. We can add what are called plasticizers. Plasticizers are simply usually small molecules that would act as a solvent for the polymer. And then what happened is you mix them into the material, and they interfere with van der Waals bonds. Now, solvents will cause the polymer to swell, increasing the volume between the space around the molecules and making it easier for them to move. Larger molecules that you put in may not cause a swelling effect, but they may interfere again with the secondary bonding between the primary polymer chains. And what happens is, as we add plasticizer, this is PVC, and so PVC at 0% plasticizer has a TG of about 200 degrees. I'm sorry, about 100 degrees Celsius. And as we add plasticizer, we can drop that TG, right? 273 is right here, so there's your room temperature. 273 would be right about here. And so at 250, we get to 30 or 40% plasticizer, we're down to 0 degrees Celsius. We'd have a 50% plasticizer, and now you're talking about minus 100 degrees Celsius as the glass transition temperature, which means PVC at room temperature would behave in a rubbery fashion. You know this, you've experienced this if you've worn vinyl rain boots or vinyl raincoat, or if you have a blow-up floaty toy for the swimming pool. And in the old days, we had vinyl seat covers on cars and vinyl on the dash. This plasticizer was part of what you got when you got the new car smell from a car. And some of the plasticizers were volatile, and as they evaporated, you get that smell. Anytime you open up a new package with an inflatable float or an air mattress, there's a particular smell. Part of what you're smelling is the plasticizer that was used to make the PVC flexible. Okay, so the key here is adding plasticizer lowers the TG because it reduces the interaction between the molecules, makes it easier for them to dance. You don't need to spread the dance floor out as much. It's usually going to raise the toughness of the material, and of course it obviously lowers the modulus because we're weakening the bonds between molecules. All right, so that's the van der Waals bonds, or the molecular interactions and the glass transition temperature. What about entanglement effects? And so we've said, we asked what holds polymers together. We said secondary bonds or van der Waals bonds. We've messed with those. We messed with primary bonds. That's our thermoset category. And now we need to talk a little bit about entanglement and what might happen here. So the simplest polymers are amorphous. That is, they have no structure. The molecules are simply randomly stacked together. They cannot form ordered groups. And polycarbonate is a very good example of an extremely amorphous polymer. It does not want to organize itself. And it's very difficult to get it to organize. into anything. It's just going to be a random mess. Part of the reason for its excellent optical properties, its really good clarity, is that it doesn't. The molecules do not organize. However, we can form kind of super entanglements. Molecules can organize themselves into close packed regions that are crystals. And so the champion of crystallization is kind of polyethylene, of the common polymers anyway. And it's perfect because it has very flexible backbone, it's very, very regular, and it's completely electrically neutral. The electronegativities of carbon and hydrogen are almost identical, but not quite. So I have essentially no polarity in the molecule. And so they can be stacked like this. We have a rhombohedral crystal structure here, and with characteristic dimensions. If you shoot X-rays at this, they diffract just like a metal crystal does or ceramic crystal does. So how does this happen? Well, what happens is the molecules are going to fold back on themselves. Most of the crystallization in polymers occurs from individual molecules organizing themselves, and then the neighboring molecules may be getting caught in that process, and they form larger clumps. So this folded chain conformation, the molecules assume why? Because they are making themselves their neighbor. They're minimizing their surface area with other molecules. And so this is a preferred kind of packing. So molecules can pack like this into what's called a lamellar crystallite. Now those lamellar crystallites will then be stacked or grouped into clumps. There will be amorphous molecules in between those clumps, and then these clumps will tend to radiate out from a common nucleus, and a collection of these radiating clumps is called a spherulite. Okay, and so this would be a spherulitic morphology, and this is what semicrystalline polymers tend to form if they're allowed to crystallize just sitting quietly as heat is extracted. Now, there's actually two major crystallite morphologies that you need to be aware of. The spherulite, which we just talked about, where you have these radiating clumps, radiating crystallites, and then amorphous material filling in. And then what's called the row nucleated, or more commonly shish kebab structure. And so the crystals have been trying to form, but if there's flow going on or shearing of the melt, say you're injecting it into a mold, then you're going to tend to break up the crystallites and you have oriented molecules with these crystalline chunks. There's your meat, lamb, and vegetables on the skewer, and therefore the shish kebab. Now, one of these is going to be isotropic, and the other is definitely not isotropic. Which one? All right, well, this is obviously going to be isotropic. I've got random orientations of everything. But the shish kebab or row nucleated structure is not going to be isotropic. I'm going to have a bunch of shish kebabs all running in the same direction, and that means I'm going to have very good properties in the direction of shish kebab, not so good perpendicular. Cracks are going to have a very difficult time growing across the stem of the shish kebabs, but they will grow between the shish kebabs much more easily. So we have anisotropic properties in the row nucleated structure. Now, what does crystallization do? Well, optically, it's going to produce haze because the crystals tend to scatter light. And so we have lots of crystals, you're going to get random scattering, you're going to get a hazy behavior. We're packing the molecules more closely together, so density goes up. Packing the molecules more closely together, so diffusion through the system is more difficult, so barrier properties get better. Packing the molecules more closely together, they're not going to flow as easily, so hardness goes up. Packing the molecules together, chemical resistance improves. So these are all physical effects. Mechanically, modulus is going to go up in general for a given degree of a given polymer. If I increase the amount of crystallization, I'm going to see lower toughness. But it's a little more complicated than that. A couple of things may be going on here as well, and we'll be talking about these. So let's look at this. This is low density polyethylene, so it's low crystallization level. High density polyethylene is a lot of crystallinity, basically different percentages of crystallinity here. Notice the modulus of LDPE is low compared to the HDPE. The strength is higher for the HDPE. So we see this extraordinary result. Low density polyethylene will strain to 1.5, 1.6%, maybe more, and then it breaks. High density polyethylene may run out. I'm sorry, this is not percent, this is total strain, so it's 140% strain. High density polyethylene may run out to 1,000% strain under the right conditions. So much higher strain to failure. In metals, that's kind of not what we expect, is it? You give me a higher strength, I expect strain to failure to go down. But strain to failure in polymers is a little more complicated, and we'll be talking about that. Now, a special case of crystalline polymers are liquid crystal polymers. And so these are pneumatic, smectic A, there's smectic B, there's some other structures as well, but these are rigid rod, very rigid molecules that in the liquid state will organize into crystals. And so if you have an LCD watch or you've got a smartphone, that screen is usually an LCD screen, and it uses polymers that will crystallize in the liquid state, and their crystal structure changes when you apply electric field, and their optical properties then change, and so you can use that to build the display. Okay, there are a few liquid crystal polymers that are commercially significant. They're interesting because while in the melt, they organize into crystals, and as you cool them down, van der Waals bonds form, and they become solid. And you get very, very anisotropic properties. You have fantastic properties in the direction of the rods, and you'll have not such good properties perpendicular. The material you're probably familiar with that's a liquid crystal is Kevlar, aramid fibers that are used for ballistic protection and protective clothing and all kinds of things. All right, what other ways can we alter the properties of our chains? Well, isomerism. Let's say I have polyvinyl chloride. If I put all of the chlorines on one side of the molecule, we can do this using catalysts or other things that you can put these molecules together in particular organizations. We call it an isotactic polymer, isotactic PVC. If the side groups alternate sides on the chain, then we call that syndiotactic, and if it's random, then it's atactic. There is no structure. Now, why does this matter? Well, here's an interesting example. Polystyrene has a TG of about 100 degrees C. Atactic polystyrene does not have a melt temperature because it's an amorphous polymer. And the beauty of having crystals is crystals melt at particular temperatures. And so if I make isotactic polystyrene, we get a semi-crystalline material. It has a particular temperature where it goes from identifiably solid to very clearly a liquid material. Now the problem with isotactic polystyrene is that crystallization is very slow, and so it's not a practical material. It's been around for a long time, but never been commercialized, as far as I know, because it doesn't crystallize quickly enough to be useful. But syndiotactic polystyrene, where the benzene rings alternate sides, has a high melting temperature, but it has a particular melting temperature. The beauty of that is if you heat it to 275, it's going to be liquid. If you cool it below 273, it's going to be a solid. It's going to crystallize, and it does so relatively quickly. So it is commercially significant material. It's at one point is a fairly significant part of Dow Chemicals plastics portfolio because it offers some particular advantages to processors because of that particular melting temperature, some things you can do with it that you can't do with amorphous atactic polystyrene. Now, if that's not enough to alter the polymer properties, we can build copolymers. And so if I'm not happy with the backbone I have, I'm not happy with the kind of van der Waals bonds I have, maybe I need more rubbery behavior, I need less rubbery behavior, whatever, we can put together different molecules. And so a very common copolymer is ABS, acrylonitrile butadiene styrene. And so if we talk about A as acrylonitrile monomer, B is butadiene monomer, and S would be the styrene monomer, how can we put those together? Well, we can build homopolymers, just all acrylonitrile, and you can buy polyacrylonitrile. It's often used in fibers in clothing. Acrylic clothing is usually polyacrylonitrile. Random, just stick them together however they want to fall together, and so you get A, B, and S in some random arrangement. You could alternate them, ABS, ABS, ABS. You could build blocks. You could put a bunch of A's together, a bunch of B's together, a bunch of S's together, and then stick them together and call it, make a block copolymer. And we could graft. So a backbone of acrylonitrile with butadienes coming off the sides instead of a hydrogen or something sticking there. And so graft copolymers. So application, I'm going to show you a case here. Take styrene and butadiene, the keys to synthetic rubber. And so styrene, here's your little styrene group, 2 carbons with a benzene ring hanging off, and here's a butadiene group. The butadiene is fairly flexible, and the styrene segment is obviously fairly rigid. Okay, and if I mix these in a ratio like this, where I've got a small block of butadienes, and I throw in a styrene, and then I repeat this over and over again, we end up with a SB rubber that's soft. If we change the basic relationship so that I have a bunch of butadiene, then a long segment of a long segment of styrene, then a segment of butadiene, and then another long segment of styrene. So now I'm talking essentially these ends, 2 styrenes for every butadiene, and we get a very hard rubber. So we put hard segments in at a higher ratio, we end up with a harder material. Okay, so that's copolymers. And then finally we can blend polymers. So maybe polycarbonate doesn't take paint well. So if I mix it with some ASA or ABS copolymer that does take paint, then I get a material that has polycarbonate properties that will also take the paint. But the key here is, if I have 2 molecules, let's say the green one and the white one here, they never connect. They're entangled together. They may phase separate. There may be partial separation. We'll look at an example of that in a second. But they're not connected to each other by anything except van der Waals bonds. Okay, so this is a blend, mixture of 2 components. So high impact polystyrene is a blend. We have the polybutadiene phase here that is in fact a mixture of styrene and polybutadiene, and then it's surrounded by styrene matrix. Okay, so this itself is a blend, and then it's blended into the styrene matrix, so you get interesting properties. Okay, and so that pretty much wraps up our basic structure. A couple questions for you. The backbone of a vinyl polymer is, you should know, all carbon single bonds. We're just going to play with the side groups. Okay, the things that can hold polymer molecules together, which is the most temperature sensitive. Primary bonds aren't affected much. Entanglements are physical, right? As long as the polymers aren't broken down, they're not going to be affected. It's your van der Waals forces that are going to really be sensitive to temperature. And so that's how you're going to see the temperature sensitivity of polymers. Thermosets. What of these is true? Connected by primary bonds and reshapeable. Connected by secondary bonds. Reshapeable. Are they connected by primary bonds? Not reshapeable. Obviously, if you have primary bonds, you cannot reshape the system. All right, so that's the basics of the structure of polymers. And so next time we're going to try to connect all those structures to the properties of the materials. All right, till then.